Thank you, Anko. Thank you, Dheeraj, for having me. Thanks everybody for coming on this holiday apparently in India. I hope to make it worth your time as well. So today I want to talk about cross-platform programming at ThinkCell, about the lessons we have learned. And before I show you my slides and give my talk, I'm very curious what experience people here in that meetup have. So have you done cross-platform programming? What are the challenges you faced? What did you find difficult about it? So maybe you can share a little bit of that first, and then I can try to focus maybe a bit on those parts of my talk. So is there anybody who has something, a question maybe? Okay, one not done. That's easy.
Dheeraj, can anybody unmute and just pitch in?
Yes.
Okay, thanks for that. Yeah, please feel free to unmute and maybe you can say what you have to say.
Hi, I work at a VR company, and our work as far as cross-platform goes looks at different kinds of VR headsets. So something on Quest, something on Android, something on Windows, and so on. And the issue that we ended up having every now and then is trying to write code in such a way that it compiles everywhere. One interesting issue that we had was with if-defs. So I could use the hash else or hash elif in Windows, but then the same thing stops compiling in Android. So those kind of smaller issues here and there, that's been our only pain points, at least.
Okay, but yeah, okay. And you think would you say that has been your approach to cross-platform programming, that you would have a lot of platform-specific differences that you handle with pre-compiler if-defs?
Yeah, so far that's been the approach that's been preferred.
Okay. Good point. I'll come to that a little bit. Yeah.
I'd like to share one experience which I have. Usually I worked on Linux server side. My servers usually tend to be big because we ingest a lot of traffic. But there has been one such feature where we had to deploy a client at a thick client on a Windows end user's laptop, and that needed some sharing of code. But unfortunately, it was so that people just wrote the code 2 times, once in Windows and once. That was a bad practice actually, but there were some parts where it was depending on platform dependent things like dealing with file or invoking an encryption or decryption algorithm, and that was not well engineered at implementation because they actually dependent on platform specific facilities, and it was mixed up with the rest of the application. So I had it was late, right? Review comments means you're late. I actually gave a quick 5-minute lightning talk at CppCon 2021 on around this on code review. So code review is late. If you give a comment on code review, you're already late. You missed the train. That's what I say. And so I gave some comments and it was done to some extent, but the real generality of the implementation was not quite there at that stage.
Yeah, okay, you can't fix that in a code review. Yeah. No, that's too big. Yeah, good point. Yeah, code sharing, Windows, Linux, encryption facilities. Yeah. Somebody wrote something in the chat. 1 second, did I see that? Okay, separate iOS and Android. Those were very good points. I'll come to that. Is there anybody else? Otherwise, I'll start. No, nobody's coming forward.
I have a friend. Sorry, just a small one. It's not C++ code. They are more into app space using Ruby, but they have to do for mobiles. They have to do very specific things for Android and iOS. And what I get a sense is usually the software engineering around doing it smoothly is not there. I guess the options are, I don't know very well about that space, but either the ways of doing things are so different that you just have to do that, or maybe there could be some better engineering ways to provision for this variation?
Yeah. I think I have no experience with Android or iOS actually, but I do know that Dropbox used to have a cross-platform toolkit in C++ that then interfaced with via Java native interfaces for Android. So they had their cross-platform implementation in C++, and they, I think, generated interfaces for it from different languages. And that looked to me like the way you should do it as a C++ programmer. But I think they stopped the project, and maybe, and that's horrible, but that's maybe the way it is, because it was too hard to find C++ programmers. So in the end, it was much easier for them to find Android programmers who know Android but don't know C++, because I think, I don't know, is it still Java? And iOS programmers who knew Swift and Objective-C but also know C++, than to find a single guy who could, do all three of those things, of course. I mean, you have to do some Android and some iOS development, and then the C++ is the backend. Yeah,
that is an unfortunate reason. It also brings me memories of something which happened earlier this year, in February this year at my place, where we developed something, a utility to be used all across all components. We are many components in microservices, etc. So something had to be done by every component, in and out, for every exchange that we do. And we wrote a C++ library because performance. But Java had to interface with it with JNI, and there was Go also, which had to interface using a C API. And it was all finally a little discouraging because we used span, and people don't know about span, and the inherent comfort is not there because it's not around for many years. So we used span, and that was a deterrent, in fact, for people to like it. And this is something that I would like to also get from your talk is, it's a fine line how you go, but I would like to see, have your opinion on whether you can share this artifact library in C++ with Go and Java and the C++, the native also, and have one development do and one enhancement apply to everybody and reap the benefits of reusing, versus there was a lot of discussion on, no, let's build that in Java also and Go also and C++ also, versus thrice the development time, etc., go to market it. And how do you balance these forces?
Good point. That's a good point, and I think I can answer that right now because I don't have slides on it. So since we ported to the Mac, we needed to write a macOS user interface, and naturally that requires some Objective-C or Objective-C++ because you have to interface with the Cocoa libraries. But we decided immediately to write our own very little, very small UI toolkit, essentially, where we could say, okay, here's a dialog. It has an edit box. It has a RTF text field maybe, and an OK and cancel button. Our UI requirements are pretty simple, I have to say. So we have very few dialogues. So it wasn't, that's why it wasn't a huge project. I mean, our application is not Photoshop, which has all these huge complicated dialogues where you have to preview your image filter or something. And we wrote two backends for that. We wrote a Windows backend and we wrote an Objective-C backend. And the code that is an Objective-C or Objective-C++ is very minimal. We wrote, essentially we wrote a C interface, C++ interface for Objective-C, where you maybe we write C++ interface for a lot of the Objective-C classes. So if you, I don't know, can create an NS string, and I think the NS string maybe has an initializer that takes a character pointer, then we would actually have a corresponding C++ function that says something like NS string underscore alloc underscore init with C string. And we would, so we can put more code in C++, where we know how that works and where everybody at the company is familiar with. And I don't have to explain them how Objective-C works. And we have our own little smart pointer type, so we can handle those reference counted Objective-C types from C++. We don't forget the reference counting, and so we try to make that really comfortable in C++. And
so lifetime management, I guess, and the interface being minimal, I guess, are the top worries on this space, I guess.
Yeah, so keep as much as we can in C++. So that's what we have. We have generic algorithms that everybody is familiar with, that we want to use, where we have our own ThinkCell library with more algorithms that are non-standard. And we want people to use those and not reinvent the wheel in some other language. And so we did that for Objective-C, and I'll come to that in my talk. We also have a small web application that ships as part of our product. And there we came to the same result. We wrote it in JavaScript or TypeScript first, and it's tiny. It's maybe 1,000 lines or a bit more. And I had to program a very simple algorithm. I had a list of data values, and I wanted to make them unique, to get the unique values out of that list. So I wanted to sort it, call make unique, and then do a binary search. And I think none of those things worked really well in JavaScript. It was super annoying. I had to program my own binary search, and you maybe could download one from the Node package manager, but the first result that it gives you is not correct. So that was a bit disheartening, I would say. And I know that the C++ standard implementation is correct. So there we came to the same result and said, okay, how can we do this web application in C++ with WebAssembly? Again, because that's what we can do, that's what we're familiar with, and how can we build a tool that makes that possible? And I'll mention that at the end of my talk. So very good points. I have a few questions from you, and that's great. And then I think I'll start, and I think we can discuss the individual issues when I come to them in my talk. All right. Okay. Perfect. So let me share the screen. Here it is. Okay. So you're seeing that all right?
Yes.
Yes. Okay, great. Okay, so I want to share the lessons we have learned when we ported our software from Windows to macOS and now in small parts to the web, as I've just mentioned. Now, what was the problem that we started with? We had been doing about 12 years of development on Windows only when we decided to port our software to macOS. And in that time, we had written about 1 million lines of C++ code. And you can imagine that in our code base as well, we had used Windows data types, Windows API calls everywhere throughout our code base. We hadn't really thought about porting our software ever to another operating system. I think when we started in 2002, there wasn't any other operating system that it was worth porting to, that anybody used. To make matters a bit more complicated, our product is an add-in, which is dynamically loaded in PowerPoint and Excel. And that has some important implications for us. It means that we are not in control of the main application. And unlike people, maybe like Ankur, who develop server applications, we don't control the computer itself either. It's a desktop machine that we share with a lot of other programs. That meant we had to be flexible in some important regards. For example, we have to be very flexible regarding the objects we can render into. We have to render into anything that the main application would give us. So for example, we have to render into NS views or core animation layers on macOS. We have to render into H windows or DirectX textures on Windows. We always wanted to have a renderer that supported DirectX on Windows and OpenGL on macOS, because that's just what we felt was best supported on each operating system. We don't share the main message, the main event loop, or we don't control it. Sorry, we do share it with the main application, of course. And we always wanted to be very quick in supporting platform-specific features that our main application supported. So we could have the least amount of friction between using the main application and our parts of the add-in. And that could mean different things. It could mean very small things. For example, PowerPoint on macOS supports a triple click that would select the entire paragraph of text. And then we wanted to support that as well. But it could also mean bigger things, that PowerPoint on macOS, for example, runs in a sandboxed environment. And that means we are running in a sandboxed environment as well. And now when we started porting ThinkCell to macOS, of course, we were looking for some cross-platform toolkit that would just hide all the platform specifics from us and would behave identically on each platform. And my talk is largely about why this does not exist and why I think it cannot exist in that way. And I've structured my talk, so I'll go over a couple of different problems that we encountered, and I'll show you how we solve them. And that will also show you to what extent we sometimes go to solve those problems. And I think some of those solutions are hopefully interesting to all of you. So first, I'll come to essentially the most important thing when you're developing cross-platform software. So at some point in your code base, you have your operating system that you have to interact with, and you want to have platform independency ++ on the other extreme. And in between, you need to have some kind of interface. And the question is, how should that interface look like? There is not a single answer to that problem. The answer depends on the semantics of your code. It depends on your problem, to be exact. I checked. No, somebody has unmuted his microphone. Okay, thanks. I checked our code base and looked for examples. How did we write cross-platform interfaces for different problem areas? And I found a few cases where that was super easy, and they all have something in common. So one easy example was, for example, our rendering engine with the different DirectX and OpenGL backend, where we, in our cross-platform C++, our rendering code, would simply create lists of triangles and texture coordinates, well, the output of any rendering API. And then you can have two different backends that just read that data. I don't really care about what they do. They just read that data and output OpenGL commands or DirectX commands. So the interface was the data structure, actually, that we would provide. Another very simple case was doing HTTP requests in a cross-platform way. We want to do HTTP requests using the system APIs because we want to make sure that the requests that we do use the configured proxies and the system settings that some system administrator might have set. And I know that the system APIs on Windows and macOS will respect those settings. And here again, the interface was very, very simple. It's a function essentially that takes a URL, maybe with some arguments, as input, and it returns a string data as the return value. I really don't care what happens in between. That is a complete black box that I can hide in the interface. And the third example was starting child processes and setting up some I/O mechanism so I can send data to child processes and read it back. That too is a black box as long as I can talk to the result I get back is a child process handle that I can send data to. What these all have in common, I kind of implied that in my phrasing, is that these were simple cases because they have so clearly defined data that goes in the interface and data that comes out of it. And I can write an interface that takes data and returns data and can treat what happens in between as a black box that I don't have to know anything about. So these are the easy cases. These are the good cases. Now, of course, there are the harder cases. For example, how can I interface with files? I can create files, I can move files, I have this file handle, and this file handle always behaves in some platform-specific way. So let's look at a very simple problem. How can I rename a file? So I looked at the documentation of the different operating systems that we support and enumerated the different ways there are to rename a file. So on Windows, there's the moveFileX API that, of course, takes the source file name, takes the target file name, and it takes some flags. For example, we can tell moveFileX that copying the file would be allowed when we want to move the file to a different volume and it has to copy. And optionally, we can also say it is okay to replace the target file. But this is not the default behavior. By default, moveFileX would return an error that the target file already exists. On macOS, so the Darwin system under macOS, and Linux, there are two rename functions that are kind of similar to each other, but not to moveFileX, because they support entirely different options. They support the option to swap the source and target file atomically on supported file systems. That sounds like a useful functionality that Windows doesn't support, unfortunately. Optionally, here we can also say that we want to get an error if the target file already exists, but it's not the default behavior. And then there's a third option that only exists on macOS. There's a CppIndia API call that has an entirely different set of options yet again. For example, in CppIndia, we can specify if we want the CppIndia call to copy the access control list of the file from the source to the target location. That sounds like a super useful functionality. If you have a file system that supports access control lists, that's a very valid question. Do I want the ACL to be copied or not? And CppIndia allows me to specify that. I'm not sure what the other API calls do actually. So here we can say copy the ACL or don't, copy the data or don't. Again, fail if the file already exists. And last but not least, remove the source file. So move the file essentially. Okay, so how do we write a unifying interface for those three very different calls? We essentially have an answer to that because the standard answered this for us. And the answer is this. It's a function that does none of all these things. It does so little that I find it hardly useful at all. It renames the source to the target and it will always override it. And I don't know how that will ever be used. And that's all the standard could specify. It's like the least common denominator of all the rename functions that some operating system supports, because of course that's what the POSIX standard actually supports, this simple rename function. Okay, but now we ended up with something that I find hardly useful. Our operating systems could do so much more interesting and powerful things, which we might need, and that we have to expose in our code. So how can we do that without littering our code with if-debs, which make code very hard to read and hard to maintain? So, okay, now we're convinced that it's pretty hard to get identical interfaces to such low-level calls like renaming a file on different platforms, just because they are so different. I would argue that we don't actually need a cross-platform file rename function. It's not something that we have to abstract because it's the wrong level of abstraction. We have to think about the problem in a different way. We need functions that do higher level things. I need a function to download a file to a cache in a thread-safe way, so no two processes will ever see a partially written cache file or read a partially written cache file. I would need a function to create an application settings file that is specific to the current user. I would need a function that can create a temporary file that will be automatically deleted when all the readers shut down, but which can be opened by other applications at the same time. Or I would need a function to create a document in a user-specified folder, which would mean opening a system-specific save file dialog, creating a sandbox exception, etc. So we need functions that have very strong semantics, and then we can implement those with identical semantics on different operating systems. Let's look at two examples. The first example is the simplest example. How can I create a user-specific application settings file? What can we do on Windows and macOS in our case? Well, on Windows, there's a natural choice to put that file into app data and then maybe in a ThingCell subfolder of app data. That already implies that we made a Windows-specific choice because the app data folder is roaming. That means if your user profile is stored on a server, that ThinkCell app data folder will be copied to each client that you log on to. That's useful for our settings file. We want the user to have the same settings on every machine he logs onto. But it's a Windows-specific design decision we made here. And then on Windows, processes can run under different integrity levels, even if they run as the same user account. That means that if the process runs under a high integrity level and he saves the settings file, and it runs again under a lower integrity level, then it cannot read the settings file we have just written. So maybe it's a good idea to encode the process integrity level in that folder name, so they get just different settings as a workaround. On macOS, we have very different design decisions to make. By default, we could say, let's store the file in library application support ThinkCell. Or maybe we know that our application is sandboxed and it's part of a group of sandboxed applications that should share the same settings. And then we could place the settings in a subfolder of library group containers that is specific to our application group. And then because we know what the function is supposed to do, we know the semantics of the function, and those semantics are descriptive enough, we can implement some default behavior just because it makes sense. For example, we could always say when we create that settings file, we want to obtain an exclusive lock while we're writing that file, because nobody should read a partially written settings file. And last but not least, we could always say we want to inherit the access control list from the parent folder, because that parent folder is a system folder and it presumably has the correct access control list set. Now, a more complicated example is how to create a temporary file that will be automatically deleted when the last user closes, but which can be opened by other applications at the same time. On Windows, there's a very convenient create file call. We create a file, we give it a path in the temp folder. We can specify a lot of Windows-specific settings. We can create the security attributes for Windows. Maybe we want to prevent the file from being executed. We want to make it accessible by the current user only. We can mark it as being temporary and hidden. And last but not least, there's this magic flag, file flag delete on close, which pretty much says what we wanted to say. It says, when the last handle to that file is closed, please Windows delete that file automatically. Good. So we have already almost implemented the behavior we wanted, just thanks to that Windows functionality. On macOS, there's no such thing as delete file on close. We have to implement something ourselves. But again, we have a pretty clear description of what the function is supposed to do. So we can choose a completely different implementation. We could go the simple way first, and we open the file in the application group, because we know the file should be shared between several applications. Then there are macOS specific things we have to do. For example, open can be interrupted by a single signal, and then we get an interrupt error. We have to try the open again. And then we can say, okay, just to implement the semantics of the function, we could implement some manual reference counting mechanism on those temp files we create, maybe in shared memory. And that would satisfy essentially the contract of our function. We can also say maybe that's not robust enough for us. For example, if one of our application crashes while it has a file open, then it cannot decrement the reference count and we somehow leak the temp file. We will never clean it up. Maybe that risk is real. Then we can say, well, we know the function is supposed to do. We could implement this in a completely different way. We are free, for example, to say, well, let's not actually create different temporary files. Let's create a single SQLite database, for example, where we store temporary data and return some file-like interface to data in that database. And now we only have one file to clean up, for example. So if one of our processes crashes and our reference counting gets out of sync, we at least know there's a single file that we have to delete and clean up. So that's the freedom we get by specifying high-level semantical interfaces. So that's what cross-platform interfaces need to look like. Well-defined, strong semantics. If you have an interface that has very weak semantics, where you don't quite know, where it's not clear how you should implement that on any operating system, then you always run the risk of introducing subtle errors. And you notice that when you start looking in the implementation to find out what's really going on. What is this function really doing? And then you dive in and see, okay, what settings does that set on the different operating system? Because you know that Windows requires you to specify this, and Linux requires you to specify this, and you don't know what the function should be doing. If you go the other way and you have very strongly defined cross-platform interfaces, then you get a lot of degrees of freedom as an implementer, and that's a good thing. So there are two mistakes we can do as programmers here. We can try to introduce those platform abstractions at a very high level. And that would mean we miss the chance to unify some code. That's very rare in my experience. We are very lazy as programmers. We typically do the opposite mistake. We introduce cross-platform interfaces at very low semantical levels, like rename, for example. And that always results in interfaces where we force some interface on very different things, where on one operating system, the interface we implement doesn't actually match the operating system semantics. So if you're familiar with Qt, I found there's this QFile set permissions API that lets you set file permissions. And it has cross-platform interface. But that cross-platform interface is the Unix permissions model, where you can set those readable, writable, executable flags for user group and other. And they just implemented that interface somehow on Windows, which you can probably do because the Windows security model is very, very powerful. But you have not actually written an interface to the Windows security model, just a small subset of it. Or the alternative problem is that you lose a lot of the expressiveness, as we've seen in the rename example. So in the end, you end up with a cross-platform rename interface that does none of the useful things that your platform-specific calls could have done. Okay, so that's like the first part of my talk. How do we write cross-platform interfaces? And I think that also probably fits somehow to the question that Ankur had. How would we write cross-platform interfaces for encryption, for example? Where I can also imagine, and I think we probably have at least some, maybe not encryption, but some verification, signature verification code, which I can imagine fits the data in, data out model pretty well, where you have something that you want to encrypt and you get out the encrypted data model, and you don't really care for what happens in between. So are there any questions regarding the first part? How do we do this and that? You can just ask. No? If not, then I'll just continue.
Quick one.
Yeah.
How frequently is something like code generation used for these kind of things? So I've seen a lot of code that has C++ generated using Python files, using Cython files. So is that something that would help in this case?
We do have some code generation, but not really for cross-platform interfaces. No, because here, I mean, the points that I would, so code generation we do when we have something that is really a very simple automatic translation. Say you have, I don't know, you have an interface specified in IDL, and now you have to translate it into C++, but transform it slightly so the IDL compiler doesn't do it. Or maybe you take the IDL and generate your implementation directly because your implementation always looks the same way as well. So these are things where we use code generation, or we use some scripts to generate the interface code. But here in what I described here is really a process where we thought a lot about what actually needs a cross-platform interface. So a lot of times what I experienced when we did this, and it was something really, I think once I held the talk and somebody commented on Twitter, that's a talk of people who did cross-platform programming for the first time. And yeah, that's exactly what it is. But I think we learned some good lessons. We discussed a lot of the times what needs a cross-platform interface. And sometimes you discuss this and you find out, well, I don't need a cross-platform interface for this at all, because the code is so different, it does so different things that it is in the end just platform-specific code. And in the parts where it needed a cross-platform abstraction, we thought very hard about how that should look and what is it actually that our application requires. So what's the cross-platform interface looking like? And what is the platform-specific implementation below? So that's where a lot of thinking goes in and not a lot of code generation.
Okay.
Yep.
Thanks.
Sure. Okay, so when you're programming, sometimes you actually have to interact with objects that that your operating system hands you, that can have very different behavior and very different lifetimes on your different operating systems. One such case that we encountered is the implementation of shared memory on Windows and all Unix systems, essentially. We use shared memory to implement inter-process communication. I said initially that our application is an add-in to PowerPoint and Excel, but that's only part of the story, because there are really quite a lot of processes involved. There's a small web application that can talk to PowerPoint. There are different processes that do, for example, OAuth authentication, so we can import images from Getty. There is a chart scanner that uses image and text recognition techniques, so we can get the data out of a screenshot of a chart that you might have in some PDF report. And it really reads the labels, evaluates how high are the bars in a bar chart to get the data out of that image. And there's also a command line process that can take a template presentation and data in some JSON file that you might download from the internet, and that can generate new presentations out of that. So maybe your monthly report that is fed with some data out of some database. So all these processes have to communicate with each other, and they do that using shared memory. And we use Boost Interprocess because that offers a common API for shared memory on Windows and POSIX. And Boost Interprocess implements everything that you really need to do shared memory. So there is a named memory object that can be mapped into the different processes that should see the same memory. There's a pointer for shared memory. So if you have your shared memory segment that will be mapped at different addresses in your participating processes, that means that you can't store an actual pointer in that shared memory, because that pointer will be wrong in the other processes. And that's what Boost Offset Pointer solves for you. Boost Offset Pointer is a pointer that can be stored in shared memory, because it actually stores not an absolute pointer, but it stores an offset to itself, which is then correct in all processes. And last but not least, you have some synchronization objects, of course. So then you can implement your little shared memory application. This is a bit how that looks like. So maybe you have a server process that creates a shared memory segment. It first has to create a name for that shared memory object. That name has to be very specific, maybe to the version of your software, to your host, to your security identifier, because the shared memory object might live in some global namespace. And then you create that shared memory object with the name and a given size, and you can construct an object in that shared memory. Here, just a pair of doubles and ints. And then you have a child process that looks up the same named memory object by name, and again finds the object and finds the pair we have just created in a different process. So now let's say I run this. I run the server, I run the child process just to test things, and I terminate them both. And now I run the server again. What happens? Well, surprisingly, it will return an error here and say that shared memory object already exists. And that's kind of surprising. I mean, I just terminated the objects, terminated the applications. Why does my shared memory object persist? It's especially surprising if you're coming from Windows, because it means that Boost Interprocess doesn't use the Windows shared memory implementation. The Windows shared memory implementation looks like this. If you want to have shared memory, you can create an anonymous file mapping. So you can create a file mapping that is only backed by the page file. And that's a great feature because it means that if the last handle to that file mapping is closed, then Windows will clean the memory for you and the file mapping will cease to exist. And if you reestablish it, you get a clean slate of memory. That's a great feature. It solves a lot of headaches for us. The memory is freed, you get new memory. That's a feature you want, but that's not the feature that is supported on POSIX systems, actually. POSIX systems have a very different shared memory implementation that seems to cause quite a lot of problems for people. So I encountered this problem, I looked for solutions, and all I found were people who had the same problem. I end my application, I restart it, my shared memory still exists. How do I clean this up? On Windows, shared memory and mutexes and many other kernel objects are reference counted. That means when the last handle to them is closed, then the resource is freed automatically. On POSIX systems, shared memory can be either file backed, which means that the backing file will still exist if the processes crash. Even after a system reboot, those files might still exist. Or there's an actual POSIX shared memory implementation, which is very limited and not frequently used, but it also has the problem that the backing memory will persist at least until the system is rebooted. So here POSIX assumes that we have a server-client model where the server owns the shared memory object, and when the server is restarted, it can just delete the old one and create a new shared memory object. But that's not the model that we have. That's not our application model in our ThinkCell application. And I could find 2 solutions to this problem, or rather, as you see, 1.5 solutions. And neither Boost Interprocess nor Qt implement them. So here we had to come up with something ourselves. So let's look at the 2 solutions to see what we did at ThinkCell just to fix this problem for us. There's one feature that could help here. These are called robust mutexes. A robust pthread mutex is a mutex that you can declare as being shared, first of all, which means that the pthread mutex can be stored in shared memory. And then you can mark it as robust as well, which means that the pthread mutex stores bookkeeping data. So it keeps track of who has last locked it and is that process still alive. So that if you try to obtain the lock, it can tell you, oh, my old owner is dead. That means it crashed while it held the lock. And then you know, oh, okay, my resource that I'm guarding here is in an undefined state, and I have to clean this up somehow. That's, of course, only half the solution, because it could still mean that the other processes crashed while they didn't hold the lock, but it helps somewhat in cleaning this up. So there's a Boost Interprocess pull request that wants to get support for robust mutexes into Boost Interprocess, but that needs some support if you're interested in that. There's one other solution. So the only resource that I could find on macOS that has process lifetime are actually file logs. So file logs are cleaned up if your process dies. And file logs on POSIX systems are super weird. There are a lot of things you have to be careful of. And there's also some Boost Interprocess pull request here by us that uses file logs. And what did we do? So what's our solution? So that Boost shared memory object has some very internal method, and that internal method actually creates the backing file. And we changed the implementation of that function, or created a new version that has a different behavior. So when we create the backing file, we try to obtain an exclusive lock to that backing file without blocking ourselves. So if that succeeds, then we know, okay, we are the first process that tries to open that backing file. We are the only one who does so because we have now an exclusive lock. So we can truncate the file and delete the old data. And then we get a shared lock and we go on with our process. If obtaining the initial exclusive lock failed, then we just wait until we get the shared lock. So that solves our problem elegantly. It just has two small problems. This call down here is not actually atomic. It will first release the exclusive lock and then obtain a shared lock. That is not actually such a big problem, I think. There are only two things that can happen that we can analyze here. So one of the things that can happen is that it releases the exclusive lock, and then another process comes along and obtains an exclusive lock while we are waiting down there in flock. And that just means that the file will be truncated twice, and that's not so bad. And the other thing that can happen is that while flock has released our shared lock, this line succeeds first, and that's also not a big problem. It just inverses the order in which we get those shared locks. So I think that works. It has worked well in practice. And here you see that we were aiming for strong and identical semantics on different operating systems. And in this case, that meant that we wanted to have strong guarantees from our operating system. Strong guarantees are almost always good. And what the Boost Interprocess API did by default was that they sacrificed strong guarantees that they could get on one operating system just to gain an identical API. So they had two choices: implement the Windows behavior on POSIX, which is hard, or you have to make some compromises. So you can't really do this for everybody, or to implement the less powerful model on Windows. And that's what they did, but that's what wasn't very useful to us. And here we had to implement those strong and identical semantics and those strong guarantees. We had to implement them for ourselves because the existing toolkits couldn't do this for everybody, just because we knew our constraints and we knew that we can live with the limitations maybe that this approach might have. Yeah, again, if you have questions now, feel free to ask. Maybe that wasn't. If I should explain something.
Sebastian, I have a question.
Yeah.
You mentioned that opening the same file twice would result in truncating the file contents.
Yeah.
And isn't that loss of data?
No, it's not loss of data
because for you, or
it's not loss of data because you're still waiting down here. So the first process obtains the lock, truncates, comes to the flock, releases the exclusive lock, and then tries to obtain a shared lock. And in between those two calls, somebody else can come along here and get the exclusive lock. Also truncates, but that file size has to be still 0 because you are still down here.
Okay.
Right.
Right.
Because that only works because nobody else has a shared lock at the same time.
Okay. Yeah. So 0 file size is truncated to a 0 file size, which
exactly.
is no change.
Exactly.
Okay.
Exactly. And I forgot something here. File locks behave very strangely if you have your directories mounted on a networked file system, and that's an important limitation here because that might not work for everybody. What we require here is that those file locks we're talking about here are only visible on our own machine. They don't have to be visible on all other machines that have the same drive mounted, because hopefully they're not using the same shared memory backing file, because that wouldn't certainly not work. And that's an important limitation because that means something about your environment. You have to mount the networked file system with the correct settings. And maybe that's not something that every implementation can guarantee. But I know that macOS won't actually work if you have your home directory mounted as a networked file system without having local locks enabled, because that means you have no locks in your entire home directory. So that's something that I can say is a good compromise, but other people might say that doesn't work for me. Okay, now we come to something that is more C++, actually. We had to, and I'm shifting focus a bit to tools that we have built. So right now I've talked about operating systems and how they differ and what we did about that. And now I talk more about, well, we also need some tools just so that we have the same tools on different operating systems. And one tool that we needed was a tool for translating text or supporting text translation. In general, internationalization is much more than translation. But now I'm just talking about text translation. And every translation tool needs to support 3 important features. So first of all, you want to be able to annotate the text that has to be translated in your source code with some macro, with a function, so that you can extract it easily and send it to translators. And then that translation sometimes needs context for the translators so they know what you are talking about when you are talking about a proxy. And last but not least, your translation tool cannot make many assumptions about how languages work. So for example, when I first prepared the talk, I learned that Russian has a different number of plural forms depending on the number. That English doesn't have, German doesn't have. I'm not sure about any languages in India, but Russia has this feature. So if you assume there's a singular and a plural and only one of them, then your translation tool does not work for Russian already. If you have such a translation tool, then the general workflow is always the same. You have your annotated source code, you extract all the translatable text, you send it to the translators, and then they send something back in typically this XML localization interchange file format, short XLIF. And you can import that data into your project as a resource. And then at program runtime, your translation toolkit would translate the original, let's say, English text and return the correct translation depending on your currently set UI language. Now, this is something where you absolutely do not want to support different native mechanisms. That would be horrible. You want the same markup in your code. You want to have a single extraction run that finds all the translatable text. And then at runtime, you want a uniform access mechanism to get the translated text back. You don't want to have different lifetime issues where in some parts of your code base, the translated text is returned as a reference counted and a string pointer. In other parts of the code base, it's returned as a heap allocated std basic string. You want to simplify that. So there's, for example, now Boost Locale, which does all of those things. It was added in 2018, much after we have added translation to our software. And it does all of those 3 things. So there's a translate function, which also serves as the annotation in your code. That translation function supports a translation context. So if we want to translate open to German in the context of opening a file and not maybe a can of beans, then we can do that. And last but not least, it supports different plural forms in Russian, for example, that all of us cannot verify now. And then that translate function would do, as I've said before, that runtime lookup in your database of text translations. And this is 2021 now. We don't have to do runtime text lookups like this is 1995. We have const export functions. And we build a little text translation toolkit based on at compile time, based on const export functions. So this is what it looks like in short. So let's say we only support 2 languages, English and Russian. Then a translatable string is an array of those 2 text translations, the English one and the Russian one. And there's a translate function that from this array chooses the correct version depending on our currently set UI language. So that step always has to happen at runtime, but it's simply a lookup into that array. That's the easy step. The complex step is how do you find the correct array from the English text, so to speak. So that's what the lookup function does. I left it as a macro here, and I'll show you the implementation on the next slide. So that takes the English string and the translation context and finds the correct pair of English, Russian, and whatever translations that we have. And if you have those things, then you can put it all together and chain it all and translate cancel as in Windows dialogues to Russian, let's say. Okay, so what does the trans lookup function do? I already implied it doesn't do a runtime text lookup. Instead, it compiles, it calculates a hash of the English string and the translation context at compile time. So that's a static murmur hash. The static murmur hash is a 128-bit hash. There's no built-in 128-bit data value. So that hash function returns a pair, and we split the hash into two 64-bit integer values. So here we hash the string, here we hash the translation context. And then we use this hash as a compile time lookup key in a template. So our lookup table, our translation lookup table, is this translatable string map template, which takes those 4 hash values, and then it contains the correct array of the English and Russian translation. And now you can probably guess already what the output of our translation tool is. The output of our translation tool are template specializations for this translatable string map. So we have a tool that runs at build time that processes the translations, calculates at build time the same murmur hash we are calculating here at compile time in C++, and outputs a CPP file that would contain this statement. So that's the template specialization of the string map with the 4 hash values, and that contains the array where you see cancel in Russian means what we need, I think it is. Okay. So a little reminder what const expr functions can do. Most importantly, const expr functions must accept and return only literal types. A literal type can be, for example, scalars, references, aggregate types that can be initialized with brace initialization, like an array. It can be types with const expr constructor and destructor, as long as all data members and base classes are literal types. And it can be arrays of literal types too. Now, const expr functions can't be virtual. They cannot contain goto. And as of now, they can't contain try catch. I think that changed in C++23. But they may contain all if and switch and loop statements, which makes them extremely powerful. And they can contain local variables as long as those variables are initialized and of literal type. And I very much recommend the talks that Jason Turner has given at CppCon about const expr functions and about the pretty crazy things that he has done with const expr functions. Now that's easily enough, and easily powerful enough to calculate a hash of a string at compile time. So I spare you the actual hash implementation. You can take that straight from GitHub. And here you see the hash function even takes an array of its zero-terminated string, and it takes a pointer to that string and passes it to the hash function that also works at compile time. It's a template function, etc. So there are really, really few limitations on const expr functions. So here, doing a cross-platform development meant we need to have the same tools on all build platforms. And sometimes that meant we had to write the tools ourselves. Because I don't think, well, Boost Local now exists. I think there weren't that many options when we started. And the approach that we chose here to embed the internationalization, to embed the translation tables into our C++ code, has another benefit in a cross-platform application. It eliminates a lot of sources of errors that could happen. So if you store the translation files on the disk, then suddenly there are questions like, what happens if users or system administrators delete those files? Do I have to handle those errors? Do I have to live with missing translations? Or should my application just fail, etc.? So all these problems just don't exist if you just embed the translation and other resources in your binary. Okay. Another tool that we have built, again, do you have questions about that? The most C++y part of my talk? Otherwise, we can discuss everything at the end. There's another interesting tool that we have built that we've also given entire talks on, and I think it's really at the core really of what makes ThinkCell also a good product because it works well, but also what it shows how we develop at ThinkCell. We have a very powerful error reporting architecture in our application. So we use a lot of asserts in our code to check invariance, of course. But unlike the default assert implementation in the standard, for example, our asserts stay in the code even in release builds. So they ship to customers. And we continue to check all invariants even in a release build. We also check all return codes from system API calls that we do. And for each such API call, we distinguish between expected and unexpected errors. So if you create a file, for example, or if you try to read a file, it's always an expected error that file no longer exists because the user or some process just deleted it. But it's not an and you have to handle that error. It's very unexpected, however, that reading a file would return error out of paper. So we don't handle error out of paper when reading our file naturally. But if it would ever happen, we would report that error. So once we encounter unexpected behavior, error out of file, error out of paper, or any assert failing, then we might show the user an error message. But what's more important is that we send a little snapshot of our application and a little error report home to our backend server. Our backend server now can analyze that error report, the assert that failed, the unexpected return value returned from a system API call. It can check if we know that bug already, or if we have even fixed it in some release. And then it can report back to the application that encountered that error. And that application can now decide, oh, there is an update available already that fixes that bug. So I can download it and maybe even install it silently. So the user will never again see the same problem. Or we might just report back, we see this error in our database. We would like to have more information about it. Please show the user a more descriptive error message and have him contact us in case the problem occurs again. So that's an extremely useful architecture to get to find and analyze errors that might depend on the user's machine. So users have DRM tools installed. Users have virus scanners installed that might misbehave or that are just badly implemented. These are all problems that we will never find in the limited testing we can do at our office. But they occur in the wild and we find out about them. And on our end, we have a little bug reporter where we can look at the most frequently occurring bugs depending on the build we're interested in. And we can annotate in which version of our software have they been fixed. And the backend even pre-analyzes the bug reports that come in and here display what's the relevant location in our code where that bug occurred. And it groups them together by the same source location, etc. So that's finding a lot of bugs. The core of this functionality on Windows is a function mini-dump write dump that just does what the name implies. It can write a small dump of your application that at the least can include the full stack and all registers. And that results in a small dump that is about 100 kilobyte in size that we can open and symbolicate on our end because Microsoft provides symbol servers. And that means that our backend can get the full stack trace of the process in the moment it encountered this failing assert or this error code. And that lets us analyze those bug reports. So it's a lot of information in 100 kilobyte that we can easily send and store on our end. And there was no similar functionality on macOS. There is Google BreakPad and Google CrashPad, which aim to be a cross-platform error reporting architecture similar to ours. But we decided not to use that because it made a lot of very strange decisions. For example, Google decided that they write Windows mini-dumps on all platforms they support. So a little documented format, I would say. It also meant that if they write a Windows minidump that contains a Linux stack trace, Windows or Visual Studio actually can't analyze them. So you have to write your own custom analyzers for this little documented data format as well, instead of just putting it into your debugger. And that meant there was a lot of code, actually, that we would need to support if we included it in our project for, in the end, a not very powerful solution. So we decided to do something else. On macOS, binaries are in this MacOS file format, and that's very well documented. And that includes documentation for the core file format, so for the dump format, if you will. I know the situation is different a bit on Linux, where the binary format is ELF, and the ELF core file format is not so well standardized, and you have to check what the GDB actually tries to read. But all that we had to do was to write a valid Maho core file that only contained stack memory and not the full heap memory. And so it would be small in size and not 4 gigabytes or whatever. And so this is simply what we did. So if you're doing a crash reporter, the first thing you always have to do is to create a new process that actually handles your crash. Your process encountered an error, you don't know in what state it is in. It might not be able to do a lot of useful things anymore. On macOS, that's pretty interesting. macOS has this interesting kernel where you can communicate by sending messages. And one of those messages is you can send access rights to your own process to another process. So that's what we did. That's what we do. We send a message to our crash reporter that contains access rights to the crashing process. And this is a bit how this looks like. And then in the crash handler, all we had to do was to go through the core file format reference and the list of macOS system functions and accumulate all the information that we need. So the first information is how many threads did the crashing process have? What is the register state of all those crashing processes? Then you have to, sorry, that was a bit quick. So what's the register state of the all the threads? You accumulate that information. What is the actual stack memory? There's again a helpful function that enumerates all the memory regions in your process. And for each memory region, you can even ask, is that a piece of the stack memory? So we can store that stack memory in a segment in our binary file. And then it's really just writing all of that in the correct order into a single file. So all the thread state, all the memory segments, plus their actual memory segments. And the resulting file is a valid core file that LLDB can load as is. Zipped, it's about 100, 200 kilobyte in size. So a very similar size to the Windows minidump. And we just needed some more additional metadata, like the list of all shared libraries that were loaded at that moment with their start address. And when we tell LLDB then that those shared libraries were loaded in that process, then LLDB can give us a valid stack trace like Windows can. So a relatively simple tool that we have also open sourced on our GitHub that replicates that Windows functionality. And there's a little support you need to have on your backend. You certainly have debug symbols for your own software. We on macOS, we cache all the system binaries for the macOS versions that we support because there aren't actually that many. And then you can write a driver for the LLDB debugger that would load your core files, load the correct system binaries for macOS, and add them as modules, etc., so that you get the valid stack trace in LLDB. Yeah, you can check out the solution on our GitHub. It doesn't compile out of the box because there are some small things that were missing, writing a zip file, etc. But the interesting parts are all there. Sorry. Okay, so that's another tool that we just have to build because macOS doesn't support it. So now I'm already coming to the last part of my talk. I said initially that we have a small web extension, a small web application as well. That lets you import data from the Tableau.com tool. So Tableau.com, if you're not familiar, is a data visualization tool that you can connect to data sources, and then you can build very interesting visualizations, but sometimes people just create dashboards with charts. And we wanted to let people import those charts from their Tableau visualization into PowerPoint and link the PowerPoint chart to the Tableau data source. And we needed a little web application to bridge those two things. So we wondered, okay, in what language do we want to write that web application? We tried JavaScript, but that was a pretty hard no immediately. And we implemented it in TypeScript. And that looked much better. It's type safe. It has type definition libraries. That means type annotations for JavaScript libraries. So you can use those JavaScript libraries from TypeScript with type checking. But sharing code between TypeScript and C++ was impossible. And there's always a little bit of code that you want to share, ideally. So we looked at Emscripten. And Emscripten looked interesting. Emscripten would let us compile our C++ code to WebAssembly. So we could build our web app in WebAssembly with the C++ we are familiar with. But now suddenly interfacing with JavaScript lost all the type safety again. So in Emscripten, you can interface with JavaScript a bit like this, with a lot of strings. You see here, I'm creating an XML HTTP request. I'm passing that as a string to the JavaScript world. So all these calls I'm making here to JavaScript libraries are not type checked, unfortunately. They are unwrapped on the JavaScript side. And then if function open does not exist, and if it doesn't take 2 parameters, then I am out of luck. But at compile time, nobody can check here that the XML HTTP request exists, that it has a function open, etc. So that was horrible. We didn't want to program that way. So what could we do? We built our own little compiler, actually, and I've just given a talk on that project in more depth at CppCon, but I think the video is not yet available. So as I've said, TypeScript ships with those awesome type definition libraries. So this is what this looks like. So this is a TypeScript description of the JavaScript document element. And you see here, it has a URL property. That URL property is of type string. It's a read-only property, so we cannot change it. It also has an active element property that can be some element on the side, but it can also be null. And here the fourth property you see is the document title, which is also a string, but you can set it from JavaScript. And those type definition libraries are not only available for the built-in standard JavaScript libraries, but there's a GitHub repository of community-written TypeScript interface definitions for by now over 7,000 JavaScript libraries. And that includes many popular JavaScript libraries like Angular, Bootstrap, and Tableau.com in our case. So you can talk in a type-safe way with all of these JavaScript libraries. Now, interestingly, TypeScript also ships with a parser, with a compiler API. It's a parser where you can create a program like I'm doing here in TypeScript, create a program from a TypeScript source file that would instantiate the parser. And then you can iterate over the parsed source file and ask, for example, all the top-level syntax nodes. Is that syntax node in my file, is that a function declaration, or is that a variable statement? If it's a function declaration, what's the name of the function? What's its return type? What are its arguments, etc.? So we could use that TypeScript compiler API actually to parse TypeScript interface definition files and transform them into C++ headers. So we can have a type-safe C++ interface to, by nature, type unchecked JavaScript libraries. And that would be pretty cool. So that's what we did. That's what our Typescript tool does. Our Typescript tool is open source. It's on GitHub. I think the URL just changed, but that one still works as well. It's now actually called Typescript. And that Typescript tool does exactly that. It compiles TypeScript interface definitions to C++ interfaces. So you can write idiomatic C++ in order to interface with JavaScript libraries via Mscripten. So where in JavaScript, maybe you would assign a string to the title property of a document, you can write something that looks very similar in C++, and that would also be type checked. So you're not passing a number to the title property. So how does that work in a little bit more detail? So this is a bit what we generate. So this is what a header looks like. And you see here that we base our implementation on Mscripten, which lets us make calls to JavaScript that are not type checked. And we just wrap that in a C++ header that adds a type safe interface on top of those Mscripten calls. So here we know the document has a title property. We know that title property returns a string, and we know it's settable, so we can generate a setter. And by now, well, by now I should change that slide. By now, Typescript is self-hosting. That means we can parse and understand enough of the interface definition libraries. So we can actually compile the interface definition for the TypeScript compiler API ourselves. And Typescript is written using itself. So it's written in C++ that uses Typescript to create C++ headers for the Typescript interface. So the Typescript snippet I've shown you before would actually look somewhat like this in C++. So you see very, very similar. We are also creating the Typescript program here. And then we are iterating over all the syntax nodes in our source file. And we even pass a C++ lambda to the JavaScript world. And that C++ lambda will be called as a callback from JavaScript. And then we can check, okay, here we have a function declaration. How do we translate that function declaration to a C++ interface statement? And translating TypeScript to C++ can be an interesting challenge because the two languages are very different. For example, in small ways, they are different. Here, for example, that's a valid TypeScript file where I define a new type foobar, which is the union of foo and bar. But at that point, neither test foo nor test bar have been declared. That's valid in TypeScript, but I can't translate that literally to C++. We have to collect all the defined types first, reorder them in some order that is valid in C++ base classes before derived classes, for example, and then output C++. TypeScript also supports enumerations that have string values or that can even be mixed string double integer values. And that's something that C++ does not support. We support that in a slightly different way. We have a lot of customization points, so to speak. We translate that into a standard C++ enumeration, funny enum here. But there's a point in our code where the C++ world interfaces to the JavaScript world. And we can customize that to say, okay, let's define some lookup type marshal enum that tells us how do we want to marshal C++ enums to JavaScript. And in that type, we can have a map that says, okay, value foo is actually a string in JavaScript. So let's marshal it as a JavaScript string. As a JavaScript string, it's not a C++ string. And bar is also a JavaScript string. And last but not least, we also support function callbacks, which was relatively difficult because functions in JavaScript, the function that we are passing here in that JavaScript snippet, they are objects. In JavaScript, everything is an object which is reference counted. So the function object is reference counted as well. And we have to, so we can't just, let's say, pass a C++ function pointer to JavaScript and have it called as a callback. That won't work. So we have to create some wrapping code that I've hidden here in a macro that lets us specify this on click handler as a valid JavaScript function object that we can pass to JavaScript. And I'll show you a little bit how that works in a second. Well, that here has one important advantage that makes programming web applications in C++, sometimes more convenient than in JavaScript. So imagine, I don't know if probably all of you have some experience in JavaScript. So let's say this onClick handler here, that JavaScript function object. It is held by the document, it is reference counted, but it might be a function object that you have created that captures other objects. It captures your this pointer maybe. So now the document has a reference count on your function object. It holds the function object alive. Your function object captures some variables, you might not even be aware of which ones, and it keeps those alive. So that makes it very hard to understand because there's no deterministic destruction of objects in JavaScript. Everything is reference counted, everything lives for as long as you don't know. It makes it very hard to understand the state your program is in. If we are writing web application in C++, this becomes much easier. We can have a class, a struct here. That struct might have a constructor. In that constructor, it creates some button that it wants to handle. And then it registers this callback and says, okay, if that button is clicked, then please call that callback. But that struct can also have a destructor that if we are writing our web application in C++ in a WebAssembly, will be called deterministically like we're used to. And that destructor can now say, okay, I'm removing that button anyway from the website, I'm done. So please automatically remove my click handler as well. And this will work in C++, and it's very hard to do something similar in JavaScript. Okay, I'm skipping the actual implementation a bit. There are some open challenges in our Typescript tool to get us to a version 1.0. There are generic types in TypeScript, for example, which are very much like C++ templates, and I'm working on supporting those. But other than that, it's a very useful and very capable tool already. So please check it out on GitHub if you're curious. Contributions are always welcome. And with that, I am actually done with my talk.